Hello and welcome to today's introduction to Chapter 5, Unit 5 on Work, Energy, and Power. So today we're going to talk about work specifically, and we will get rolling. So work, definition-wise, is the product of the component of the force along the direction of displacement and the magnitude of the displacement. Simplified, work is equal to a force multiplied by the distance the force is exerted over. So work equals force times distance is the equation we're going to use. Work is done on an object when a force causes the displacement of the object. So if I push something and it moves, I've done work. If I push something and it doesn't move, I've done no work, regardless of how hard I push. Again, work is not done unless the object is moved with the action of the force. So the force has to move the object in order for work to be done. All right. And then if we have an angle, and the only work that is done, the only components of the force that matter are the ones that are going parallel to the displacement. For example, if I'm pulling this box with a force here, the only part that I'm concerned about is going to be this component up here. And so the easier way to work that, so the force is perpendicular to the displacement, it's going to be 0, so we don't get anything. If it's parallel to, it's going to be 1, and so we get force times distance. But it's going to be FD cosine theta is going to be the equation you use a lot with forces at angles. And so again, cosine of 90 is 0. So if it's perpendicular, if I have a force acting here, it's not going to move anywhere. Likewise, if I have a force pulling in this direction that the black arrow here is pointing, all of that force is going to be in the same direction as the motion of the object. So that is going to have a magnitude of 1. And so the cosine of 0 is 1. And so let's do some practice. A couple quick other things, I guess. Work has dimensions of both force and length. So we're talking units here. So units for force are newtons. Units for length are meters. So the SI unit for work is a newton meter, or we've simplified that, which is the same as a joule. If you struggle remembering that work is in joules, just think if you want to buy a joule, you have to do work to get money to buy joules. So work gets you joules. And so that is a unit there, which is equal to a newton meter. For perspective, if you take an apple, average size apple from your waist, and place it on top of your head, that's doing about 1 joule of work. So that gives you a little bit of an indicator of what a joule is. All right, so these three questions. Is work being done? First one, a student holds a heavy chair at arm's length for several minutes. Is work being done, yes or no? And in this case, it's not because he's holding it. He's not moving anywhere, he's holding it. So there's no work being done. Carries a bucket of water along a horizontal path while walking at a constant velocity. His force is going to be in the vertical direction. He's walking at a constant velocity this way. So this is also going to be no work. A lot of effort, but no work. And then a person pushes the car along the road at a constant velocity. This is going to be work is done. So this is no. This is no. This is going to be yes, because you have to exert a force that is equal to be at a constant velocity, you're still exerting a force equal to that of friction, air resistance, all of those. And so you have a force being exerted there. All right. When we talk work is a scalar quantity. It can be positive or negative. So positive if it moves in the same direction, with the force in the direction in the same direction there, I guess, and negative when the work is in the opposite direction of the displacement. For example, if you're pushing something, or you're pushing a car, let's say, and you're pushing it, it's going faster, you're doing positive work. If you're slowing down a car, you're doing negative work. And then that's force in opposite direction of displacement. And if we apply the equation correctly, we'll see that cosine is negative when theta is greater than 90, but less than 270. So if you use the equation right, you can get your numbers out of that. But if you are helping the object to move, you are doing positive work. If you are hindering the object from moving, you are doing negative work. If the work done on an object results only in a change in the speed, the sign will tell you whether the speed increases or decreases. So if you do the equation correctly, your sign will tell you whether the speed increases or decreases. If the net work is positive, the object will speed up and the work is done on the object. If the work is negative, the object will slow down and the work is done by the object on something else. So when we talk, it had work done on it, it did work on, that's what we're kind of talking about there. All right, let's do a practice question. So a girl is playing tug of war with her dog and pulls the dog a distance of 8 meters by exerting a force at an angle of 18 degrees with the horizontal. If the amount of work the girl does in pulling the dog is 190 joules, what is the magnitude of the force? We have a girl pulling on a dog with a force of, this is 18 degrees with the horizontal. So which would be the same down here. The dog goes 8 meters. It's going to be 8 meters. And the work done is 190 joules. I want to know what this force is. Okay, so we have our equation. We have work equals force times distance times cosine of theta. And in this case, I know my work is 190 joules. I know that my distance is 8.0 meters. And I know that my theta is 18 degrees. So I can manipulate this equation. I can solve for F, so I divide everything by d times cosine of theta. And so you get 190 joules divided by 8.0 meters times cosine of 18 degrees. I need to make a better 18 degrees. Maybe. We'll just cut it all out. So cosine of 18 degrees, not 180. And if you run those numbers through, you should come to a final answer. The force was 25 newtons. And in this case, I would say newtons to the left, because my dog moved in my direction, to my picture, to the left. So there's your equation there. Here are some problems for you to try on your own. I would advise you pause this screen right now, because I'm going to give you the answers on the next one. So hit pause button, work through these, and then you can check yourself as soon as you hit play again. These are the answers to the previous questions, and this is where we're going to stop our discussion on work at this point. If you have questions, please let me know. Otherwise, I will see you as we continue our discussion on work, energy, and power.